time we were here only. That is, we have seen, we have studied that the second step of the PCM is the quantizations, where we have seen that quantization is of two type. One is the uniform quantizations, another is the non-uniform quantizations. And a uniform quantization is again divided into two categories, that is the mid-trade and mid-rise. And we have seen that what is the mid-trade and what is the mid-rise. And then taking the two examples, we have seen that how that actually the process is being actually done. That process is being completed. For that, we have taken the analog signal, which you can see is mentioned in this slide itself, because I want to just recall the things what we have studied. So the analog signals we have taken, whose maximum amplitude is plus MP and minimum amplitude is minus MP. Then actually for this analog signals we have taken the sample, because the first step is the sampling. We have taken the sample, say at this point, at this point, at this point, at this point, like that. And then the whole sample signals, whole range of the sample signal is divided into the various quantizations level, okay, whose quantization step is given by delta. So this step is given by delta. This gap is given by delta. Right? Now, then what we do, we simply compare the sample value. We see the sample value, and then we find that whether it is having the whether you are using the mid-trade and mid-rise type of quantizations. We simply approximate it at the nearby level, and then we see that that level is represented by which binary number, and corresponding to that we represent that binary number by any of the available actually representation, line coding techniques. And then since if we represented in the line coding techniques, then this is nothing but we can represent this into the electrical wave form, and the electrical signals can be transmitted. So this signal is being transmitted. Now, so here I have mentioned some mathematical terms also. That is, if L is the total number of levels, that is the dotted one is treated on the quantizations level. And if M is required to represent each, where M is the number of bits required to represent each level, like suppose if we take 4 levels only to cover the entire dynamic range of these analog signals, then in that case we need to take M equals to 2 only. Right? But in that case, what will happen? The step size, this delta, will be more. So if delta will be more, then delta by 2 will be large. It means that the quantization error, maximum quantization error, what we have seen in the case of PCM, which is one of the serious drawback of the PCM, that delta by 2 increases. So delta by that is the quantization error increases. So if the quantization error increases, quantization noise increases. So because of that, the signals to noise ratio decreases. Okay, so it is not preferable to have the less number of bits, because or less number of quantizations both are equally dependent, because L is proportional to M.
So
M increases, this L will increase. But what will happen if we increase the number of bits M to represent the each level? Then L, definitely the number of levels, the number of quantizations levels will increase. So if the quantizations level will increase, the quantization step, that is this delta, will decrease, and the quantization error will decrease. But it is not like that you keep on increasing this M to increase to reduce the to increase the number of levels, to reduce this delta, reduce the quantization error. You cannot keep increasing this M, because the certain restrictions are also there, which we will see later on. That is, if we increase this number of bits, then the bandwidth what is required for the transmission of this PCM, which is given by, we'll calculate this bandwidth, which is given by M into FM. FM is the maximum frequency of this message signal, and M is the number of bits required to represent each level. So once we will increase this M, then bandwidth increases. So bandwidth increases, it means that PCM will require the large bandwidth to transmit. So which is also having certain restrictions. Yes. The bandwidth constraint is very much important, which we must have to consider. So we cannot keep increasing this value of M. That is, you cannot think like that M is in our hand, we can increase it up to any level. It also have certain constraint on the bandwidth. So correspondingly, it means that we can say that we have to compromise the transmission bandwidth with the number of bits represented, and then we have to compromise this quantization error. And because of this quantization error, later on we will see there is a quantization noise. Because once we calculate the mean square value of the quantization error, we get the quantization noise. And because of that signals to noise ratio, which is preferable to have uniform throughout the quantization process, it is preferable to have the signals to noise ratio constant throughout. The quantization process will decrease. So it is decrease, whereas we prefer to have the high value and uniform throughout. So that is not desirable. So and these are certain drawback of the uniform quantization method. So so m is the number of bits. If you use to represent each level, then definitely L will be 2 to the power m. Then if you take m equals to 2, then it means that we are using the 4 number of levels. If you take m equals to 3, as in this case, you can see then L equals to 3, 2 to the power 3 equals to 8. It means that we need to use the 8 number of level. If you take m equals to 4, that will be 16, 0, 0, 0, 2, 1, 1, 1. Now, so how can we represent this delta? So delta we can calculate. That is the step size. Step size is nothing but the maximum dynamic range in terms of the voltage, which is given as 2 MP. Minus MP to MP is 2 MP divided by the total number of quantizations level will give us the quantization step delta. Okay. So these things you should note down because these expressions are going to use in the later in our later calculations. Okay. That is if L we represent it by the number of levels. If m is the number of bits to represent each level, then L is given by 2 to the power m, and delta, that is the quantization step, is given by twice MP by delta. Now, so to overcome the uniform quantizations, as we have seen that there are certain issues with the uniform quantizations, we go for the non-uniform quantizations. So why we go for the non-uniform quantization? And in fact, this non-uniform quantization is performed by the compounding. That is, the compounding is the device which consists of compressor and expansor. Compressing and expansing. So this compounding is the process, and the compressor the compressor compounder is the device which perform the compounding process. So that compounder perform the compression and perform the compression and expansion. So in fact, the compression is performed at the transmitting end, and expansion is performed at the receiving end. This expansion is the reverse, complementary to that of the compressing. So these two characteristics we will see. But before going to study about the basic characteristics of the compressing, expanding, let us see that why we go for the non-uniform quantizations. So if we take certain case of the uniform quantizations, like you can see, the uniform quantizations, whose we know that for uniform quantizations our maximum quantization error is given by delta by 2. I have put over here the mod because this quantization error, maximum quantization error may be minus delta by 2, it may be delta by 2. So we need to take epsilon for the better understanding. So epsilon max equals to mod of delta by 2. Where delta is nothing but the step size. In the previous slide, just we have seen that this step size is given by twice MP by L, where MP is the peak value of the analog signals and L is the total number of quantizations level. So if we normalize this MT in place of this considering the minus MP to MP, if we normalize it by the voltage 1 volt, then this delta will be simply given by 2 by L. Now, in the special case, if you consider that L equals to this M, L equals to 2 to the power M, where M is 4. That is, each level is represented by 4 number of binary bits. Then the total number of quantizations level will be 16, 2 to the power 4 equals to 16. And in that case, this step size delta will be 2 by L, that is 2 by 16, that is 1 by 8. And in that case, we can say, this we have done the assumptions, okay, M equals to 4. Just for understanding that why we go for the non-uniform quantizations rather than for the uniform quantizations, whereas the performing of the uniform quantization is very quite simple as compared to the non-uniform quantizer. Okay, so this epsilon max, that is the maximum quantization error in this particular case, becomes 1 by 16. So since we are normalized with respect to the input signal, that is n equals to 1, so we can say that this quantization error is 1 by 16th part of that of the full input voltage range. Okay, so now If we consider further, if you consider that full input voltage range is 16 volt, then this maximum quantization error will be nothing but 1 volt. Okay, 1 volt. So we can consider that this 1 volt at the maximum at the voltage range of 16 volt is quite sufficient. Actually, is not high, much high. We can assume that okay, if this much of the quantization error is coming, then it is quite low as compared to the 16 volt, and we can consider. But since in the uniform quantizer, since in the uniform quantizer, this quantization error remain constant, because this quantization error ultimately depends upon the delta only. So this quantization error remain constant throughout the quantization process. So, so what will happen? In place of considering this 16 volt at the lower value of the amplitude, like 2 volt, 3 volt, if you take, then if we say that the quantization error is 1 volt, it means that it is quite high, which is not preferable at the low amplitude. Low amplitude. For example, say if you take the input voltage as 2 volt, like the if the voltage level is at the 2 volt, then this maximum quantization error will remain to at 1 volt. That is, we can say that it is nothing but the 50% of the input voltage. 1 by 2 is 50% of the input voltage. And in this next case, if you take the V equals to 3 volt, this Emax will remain same again, and its value will be 33.33%. That is 1 by 3, 33.33%. If you take the V equals to 15 volt, its error will be simply 6.7%, and related to the input voltage. And if V equals to 16 volt, it further decreases by 6.3 volt of the input. That's why I told you that if you take the if the maximum amplitude is 16 volt, then this much of error is permissible. We can say that this error is small. But if you consider the lower amplitude portion of the same signals, we can say that up to that amplitude, this quantization error is quite high. Okay, it means that for low level amplitude, maximum quantization is relatively high. Maximum quantization error is relatively high as compared to the high level amplitude signals. So in order to have the uniform, in order to have the constant quantization error, non-uniform quantizer is used. Okay, so in order to have the uniform quantization error, constant quantization error, non-uniform quantization is used. And in fact, what happens if we consider the signals to noise ratio as by NQ? Okay, so NQ later on we will see. Later on we will see that NQ for the case of PCM is given as del square by 12 uniform quantizations. We will derive it. So this delta is nothing but the step size. Okay, so here what happens, this quantization error increases at the low amplitude. At low amplitude, this quantization error, this epsilon max increases. So because of that, NQ increases, and NQ increases, it means what? And at the same time, at low amplitude, our signal power is also low. So this signals to noise ratio, this is low, and at low power, at low level, this quantization noise increases. So this signals to noise ratio decreases. Whereas at high amplitude, this signals to quantization noise, this signal ratio is signal power is also high, and the quantization noise is also low at the high amplitude. So ultimately, this signals to noise ratio increases at high amplitude. But it is not preferable in the communications or during the quantization process that at lower amplitude quantization signals to quantization noise is less, and at the higher amplitude the signals to quantization ratio is more. Rather, it is preferred to have the high value of the signals to quantization ratio, whatever the value it is, but it should remain constant throughout the quantization level. It is highly desirable. So to get the constant signals to noise ratio, the constant signals to quantization noise ratio throughout the quantization level, we prefer to go for the non-uniform quantization. So this is the main reason. That is, to get the signals to quantization noise ratio constant throughout the quantization process, we use the non-uniform quantizations. Okay, and it is in fact achieved by the non-uniform quantization. Then question arises, how can we achieve in the non-uniform quantizations like signals to quantizations noise NQ? is constant. How can we say that? How can we get this constant? So what happens in the uniform quantizations? The signal to noise ratio is low at the low amplitude. So the first way by which we can increase the signals to noise ratio at low amplitude, our aim is to increase the signals to noise ratio at low amplitude, and our aim is to decrease the signals to noise ratio at the high amplitude, so that the throughout the quantizations process in the non-uniform quantizations, our signals to noise ratio remain constant. So to increase this signals to noise ratio at the low amplitude, what we do, what we do, because what we do, we simply actually at the low amplitude, we this NQ, we increase this NQ, we decrease this NQ at low amplitude. So how can we decrease this NQ? Because at low amplitude, in the uniform quantizations, the signal to noise ratio is low. But in the non-uniform quantizations, we try to increase the signals to quantization ratio. So how can we increase the signals to noise ratio at low amplitude? So that we can increase just by decreasing this NQ. And how can we decrease this NQ, which is given by del square by 12? In the case of uniform quantization, how can we decrease? Just by decreasing this delta. Because if we decrease this delta, then this NQ will decrease. So how can we decrease this delta? So how can we decrease this delta? That is, delta is the step size. So we can decrease this delta by taking large number of quantization step at low amplitude. So if we take the large number of quantizations level at the low amplitude, then this delta, step size, this delta will decrease. And if this delta will decrease, this quantization mass will decrease, and ultimately this signal mass ratio will increase. Similarly, in the case of high amplitude, where the signal to noise ratio is high, and our intention is to decrease this signal to noise ratio so that it can match with the increased signal to noise ratio at the lower amplitude, we try to increase the quantization noise. So if we increase this quantization noise, then what will happen? How can we increase the quantization noise? Just by taking the less number of quantization step at the higher amplitude. So how can we take the less number of quantization step at the higher amplitude? To increase the step size at the higher amplitude. So if we increase the step size at the higher amplitude, this delta will increase, and del square by 12 will increase, and hence the NQ will increase, and signal to noise ratio will decrease at the higher amplitude. So ultimately, the case may come where the signal to noise ratio remain constant throughout the quantization process. So in this process, what we do, the whole signal, all this is what I have actually told you, that I'll read it, so that once I share this PPT, you can go ahead and you can easily understand. So what happens? You can see at the lower amplitude of the signals, this quantization step is quite low. So if the quantization step delta is low, then signals to quantization noise will be low, and the signals to quantization noise will increase. But at the higher amplitude, you can see the quantization step delta is more. So if delta is more, signals to noise ratio here is decreased. So decreased, so we can choose the step size and uniformity of this step size, that is the variation of the step size at each value of the amplitude, such that the signals to quantization noise remain constant throughout the quantization process. So to make this signal to noise ratio constant throughout the quantization process, we require to compress the signal at the low amplitude level and expand the signal at the high amplitude level. So this is called as compression, and this is called as expansion, and the whole process which is performed, that is this is called as compression, and the whole process which is performed called as companding. Okay? Called as companding. So in the compression itself, this process is being actually done. That is, low amplitude signal is compressed. So it means what? If in the reverse direction also we can think, that is, if low amplitude signal compressed and higher amplitude signal expand, and then if we use the uniform quantizer where step size remain constant, then also it will look like that only. That is, it will look that at the lower amplitude we have decreased the step size and the higher amplitude we have increased the step size. I'm again repeating, that is, in the non-uniform quantizations, we take the lower step size at the low amplitude and higher step size at the higher amplitude. And this process is performed by the compression. And in compression, what we do, the lower amplitude of the signal is compressed and the higher amplitude of the signal is expanded. So if we take the, and then after that, we take the uniform quantizations. That is, in the uniform quantizations, our step size remain constant. Okay. So if we compress at the lower level, if we compress our signal and if we expand at the higher amplitude, if we expand, then it will look like that this quantization step is small at the lower amplitude and large at the higher amplitude. And at the same time, it will maintain the signal noise ratio constant. So this process is performed in the compressor. Okay, and then at the receiving end where the signal is being transmitted, at the receiving end, the reverse process of the compressing is used, which is called as companding. Okay, and the combined action of the compressing and companding is expanding is called as companding. Okay, the combined action of the compressing and expanding is called as companding. Or the compander is the device which performs the function of compression as well as expansion. So if you look the basic model of the companding, which is actually used to perform the non-uniform quantization, then first we use the compressor. Input signal gets compressed. That is, the lower amplitude signal gets compressed, gets attenuated, and the higher amplitude signal gets amplified. And then we simply use the uniform quantizer. Right? So these two steps are performed at the transmitting side, and this expander is performed at the receiving side. But since here we are discussing about the companding model, so in the single actually blocks, you can see that all these three blocks are placed. Whereas in the companding model, these two are performed at the transmitting side, and the expanding is performed at the receiving side. So ultimately, the input and output gives us the complete companding model. Now, then question arises that what is the compressor characteristics following which we can compress the input signal and we can expand the output signal. Okay. Similarly, what is the characteristics of the expander? By following that, we can expand the input signals and we can expand the low amplitude signal and we can compress the high amplitude signal. So now we are going to study that. That is the basic characteristics of the compressor and the expansor. Like this, you can see this is the basic characteristics of the compressor. Okay, which is used in the companding process. That is, this one is the compressor input. Okay, and this one is the compressor output, and it follows this type of curve. Okay? And this type of curve, to follow this type of curve is very easy because many nonlinear devices we have diode, transistors, FET, which actually gives this type of characteristics. That is, if you give the input and output, if you draw the output characteristics of the FET, output characteristics of BJT, also you might have seen like this only. So in that, if you look to the low amplitude level of the compressor input, low amplitude level, the compressor input will be this only, measure signal. So if you look to the low amplitude level of the compressor input, then this is the input voltage VIL, and this is the output voltage VOL. Responding to that, and you can see this VIL is small and VOL is large. Okay, so if you consider the gain of this compressor at the low input, then gain will be nothing but the output voltage divided by input voltage, that is VOL by VIL, which is large. Why? Because this output is more and this VIL is low. Whereas it means that it means that what it means that and now if you look to the higher actually input voltage, then then higher input voltage A2 is equal to VIH by VOH divided by VIH. And since VOH and VIH is comparable, or even VOH is less than this VIH, so this A2 is less. So A1 is more and A2 is less. So compressor perform large compression at the low amplitude and as compared to the high amplitude. Or even it perform the it compresses the lower amplitude. Similarly, the reverse process of that you can see is given by the expander characteristics, where expander gain at the low amplitude is given by A1. So A1 you can see input voltage is large, output voltage is more. So A1 will be less here because in the compressor A1 was more. So A1 should be less here in the case of expander. Similarly, A2 should be more as compared to the A1. So which is the case. Although in the graph it looks that A2 is approximately equals to 1, that is equal to the V, where in practical it is not the case. Rather this A2, this output amplitude is higher than the input voltage. So A2 here is more than the A1. Okay. So A2 is more than the A1, which is the complementary process of the compressor is nothing but the expander. And in one graph, we can represent the basic compressor characteristics and the expander characteristics, which is given by, like suppose this is the input voltage, this is the output voltage. So you can see this is the nature of the compressor. Once the input voltage is positive, once the input voltage is negative, you can draw in the same way. This is the complete characteristics of the compressor. And and this is the nature of the expansion, which you can see also verified from this figure. This is the nature of the expansion when the input voltage is positive, and just going through like that, we get the expansion characteristics in the negative voltage for the negative voltage. And the complete curve is called as compounding curve for the PCM system. Compounding curve for the PCM system. And this compounding curve we obtain by two law. One is called as mu law compounding, and another is called as A law compounding. In some country, the mu law they used to use the mu law. In some country, they used to use the A law. A law. So depending upon that company's policy, any one of the law they can use. So the mu law in some countries it is being used, and in some countries this A law is used. In India, we used to use this A law compounding techniques. Let us see what is this mu law compounding and what is A law compounding. So this mu law compounding is defined by these mathematical terms. Actually, our aim is to just get this curve only. Okay, our aim is to get this curve only. So this curve should be defined by some mathematical terms, so that just by doing the programming and all, we can compress at this by this curve. Uh, uh, as per our expectations, we can compress. So that mathematical expression is given by V out equals to formula. Formula compounding. That mathematical expression is given by V out equals to V max ln 1 plus mu. Because of this mu parameter itself, it is called as mu law compounding. So ln 1 plus mu V in by V max divided by ln 1 plus mu. Where mu is the parameter, V in is the input voltage magnitude, V max is the maximum value of the input signal. And this mu, what happens can vary from 0 to 300, 400, 500 like that. Okay. So this V, if we take the mu equals to 0, then this is nothing but the case of no compounding, no compressor, no compression, and it is the case. It becomes simply the case of uniform quantization. Mu equals to 0. Okay. Now, if we take mu equals to 255, then this 255 value is being used practically. It is being used in our commercial use. Practical value of the mu equals to practical value of the mu is 255, which is being used in the PC. Okay. So if you draw this curve itself, then and if you normalize this, because you can see this V in by V max is already actually normalized. So if you take that normalized value, then for mu equals to 0, you can see input is same, output is same, that is there is no compression. So it is the case of uniform quantization. Similarly, this mu value is, you can say, is taken somewhere in between 0 to 255. Maybe you may consider it as 100, you may consider it as a 200 actually, but this the value of mu what you take. is 255. So I've mentioned only this. That is, once we'll increase the value of mu, then the curve will shift like that only. And this value, if you take the mu equals to 255, your Mueller compounding characteristics, in fact, the compressor characteristics will look like that only. And since this mu equals to 255 is practically being used, that's why it's practically used. That's why I mentioned over here as mu equals to. Now, if you compare the signals to noise ratio, actually this is the experimental data, signals to noise ratio in dB with respect to the signal level, then if we do not apply any compounding technique, then our signals to the noise ratio with respect to the input signal level increases. As we have seen that in the case of uniform quantization, signals to noise ratio is low at the low amplitude and high at the high amplitude. So it increases linearly, almost linearly. If we apply the compounding, then our signal to noise ratio remain constant, almost remain constant, which is our which is our requirement. So we have achieved our requirement. Similarly, the similar function is performed by the ALA compounding, which is defined as Vmax A V in by Vmax divided by 1 plus A, where A is the parameter. That's why it is called as ALA compounding, as the case was for the Mueller compounding. And this equation is valid once the V in by V max, that's the normalized value of the input voltage lies in between 0 to 1 by A. And if normalized value of the input voltage lies in between 1 by A to A, then this expression is used. That is 1 plus ln A V in by V max divided by 1 plus ln A. Okay. Now, if you take the A equals to 1, as we have taken for the case of mu equals to 1, so the similar characteristics we get, that is corresponding to A equals to 1, this becomes the case of uniform quantization. That is, no compression is being used. If you take A equals to 2, then in the similar way as to that of the Mueller, this curve will shift like that. And if you take A equals to 87.56, specifically I have mentioned because this 87.56 is the practical value of the A which is being used. Then it will look like that. So this is about the quantization process. That is, we have seen that uniform quantizations, non-uniform quantizations, all types of uniform quantizations, and how we perform the non-uniform quantizations, how can we go for the non-uniform quantizations, what are the advantages we have studied. Now, our next topic is the transmission bandwidth. As I told you, that you might have studied about the amplitude modulations with carriers, say. The bandwidth of this one is twice FM. If you might have studied DSBSC, bandwidth of that also is twice FM. You might have studied SSBSC, bandwidth of that is FM. You might have studied the VSBSC, the bandwidth of that one is in between FM to twice FM, because only partial sideband is suppressed. Okay. You might have studied the FM, whose bandwidth is defined by the Corson's rule, Corson's law. Okay. So similarly, if any such type of techniques we are studying, then we need to find out the bandwidth of that particular system. So what will be the transmission bandwidth of a PCM system? So for that, if we assume M, as we have already assumed, as a number of bits binary digits to represent each level, M is nothing but the number of binary digits used to represent the each quantizations level. And the total number of quantizations level is given by L. And definitely this L equals to 2 to the power M, what we have seen. And by definition, the bandwidth of this PCM is given by the half of the signaling rate. This is the basic definition of basic relationship between the bandwidth and signaling rate. So the bandwidth is similarly we can apply the same to the PCM also. That is, the bandwidth of the PCM is half up to that of the signaling rate. Then if we are able to calculate this signaling rate, it means that we can calculate the bandwidth of the PCM. So let us calculate what is the signaling rate for the case of PCM. And since the signaling rate is defined as number of bits per second, number of bits what we transmit per second is nothing but the signaling rate. And half of that number of bits per second what we are transmitting is nothing but the bandwidth of the PCM. So the number of bits per second, in fact, we can write it as number of bits per sample. This is nothing but M. That is For each sample, what happens? Each sample is coded. Each sample is approximated to the quantizations level, and each quantizations level is represented by some certain number of bits. So if this M, it means that M is the number of bits per sample. Suppose we may use 2 bits, 3 bits, 4 bits, 5 bits, depending upon our requirement that how much quantization error we want to keep it low. So the number of bits per sample is nothing but M, and multiplied by the number of samples per second. Because if you look, it is bit per second, it is sample per second. So sample will cancel out. Bit per second and sample per second. So ultimately the unit will come out to be bit per second. So which is nothing but the sampling rate. Mhm. Which is nothing but the sampling rate. Hence the sampling rate is we can calculate by calculating the number of bits per samples, which is given by M, it is known, and the number of samples per second, which is nothing but the sampling frequency itself. Fs is the sampling frequency. Fs is nothing but the sampling frequency. Fs is nothing but the sampling frequency. So R, R, we can write it as M into Fs. M into Fs, because R is nothing but M into Fs. Hence, bandwidth of the PCM, we can write, should be slightly greater than, although the minimum value of this bandwidth is desirable, but if it is slightly more than that, then also it is preferable. So the bandwidth is slightly more than, not preferable, it requires slightly more bandwidth. Okay, so bandwidth is slightly more greater than equals to half of the R. As per the definition, half of the signal rate, so half R. And R is nothing but MFS. And since you know by the sampling properties, sampling theorem, because the first step is nothing but the sampling itself. So the sampling theorems should also be satisfied. So Fs should be greater than equals to twice Fm, specifically for the low pass signals. So if you take the Fs as a twice Fm, then 2 will cancel out. Ultimately, our bandwidth for the PCM is nothing but the MFM. So the bandwidth of the PCM is coming out to be greater than equals to M into Fm, where the minimum transmission bandwidth is desirable. Minimum transmission bandwidth is desirable, that is, if equal sign is there, then that is desirable. It is not like that if it is greater than equals to MFM, then you can take anywhere. Minimum transmission bandwidth is desirable because we prefer to have as minimum transmission bandwidth as possible. So the bandwidth of the PCM is greater than equals to MFM. So the same things I have written over here in the previous slide in the starting of our discussions. That is, the bandwidth of the PCM is given by MFM. So because of that only, we cannot keep increasing the quantizations level L, because once we increase the quantizations level, then our quantization step will decrease, and at the same time quantization mass will decrease. Quantization error and quantization mass will decrease, but at the same time it will increase the transmission bandwidth of the PCM, whereas the minimum transmission bandwidth is desirable. Okay, so this is how we can calculate the bandwidth of a PCM system. Now, in the next topic, although I have not made the slide, no problem, we are going to study the quantization noise in PCM. And I have already told you that how can we calculate basic process. I have already told you that how can we calculate the quantization noise and how can we calculate the quantization noise in the PCM, that I have already told you. Okay, so the quantization noise we all know, that is the quantization noise epsilon max, you can say, is given by M Q R. Earlier we have taken X Q and TS minus X and TS. That is, this is the quantization error. That is the difference of the quantized output to that of the quantizer input. Okay, so this is epsilon, we can represent epsilon. Okay, and the maximum value of this epsilon, we have seen that in the case of uniform quantizers, it is coming out to be L by 2. Okay, so this is the quantization error. And the nature what we have seen, it was coming out to be, I'm just giving you so that you can recall that. Okay. This type of the characteristics we got. Approximately this type of characteristics we got. In the case of quantization error epsilon, this value was delta by 2. This value was minus delta by 2. Okay, this one was delta. Especially in the case of mid-rise type of quantization. Okay, it means that epsilon max, our epsilon max varies in between minus delta by. Sorry, it means that our epsilon max varies in minus delta by 2. Delta by 2. Right? Right? But if the step size delta is very small, then over the interval of minus delta by 2 to delta by 2, if our step size is small, step size is small. If our step size is small, then over the interval of minus delta by 2 delta by 2, the quantization error may be assumed to be an uniformly distributed. The quantization error may be assumed, earlier also I told you, may be assumed as an uniformly distributed random variable. Okay, so one thing I want to clarify here, that is, sometimes we used to ask, that is, what is the difference between the quantization error and the quantization noise? Quantization error is the difference between the difference of the voltage. You may consider the difference of voltages, that of the output of the quantizer to its input of the quantizer, to the input of the quantizer. Whereas the quantization noise, what we here we want to calculate is nothing. This quantization noise, what we here want to calculate is nothing but the mean square value of quantization error. So if you calculate the mean square value of the quantization error epsilon, then we call it as quantization noise. And it means that how can we calculate the mean square value? If it is a random process, noise is the random process. So NQ we can write as expected value of epsilon square. That is nothing but the mean square value. Expected value are of knowing. So this is nothing but it is nothing but the quantization. NQ equals to expected value of epsilon square. Right? So this is called as quantization noise. Then how can you calculate this expected value? We all know that expected value is given by integrations over epsilon square and then f epsilon d epsilon. This is the basic differences which we have already studied in the probability and random process. To calculate the expected value of random process, that is the bracket one comes out to be here. So here our aim is to find out this f epsilon. So until unless we don't have this f epsilon, we cannot find out this NQ. So how can you obtain this f epsilon? F epsilon, as I told you, is uniformly distributed. So uniformly distributed signals we can take, and it is uniformly distributed over the interval of minus delta by 2 to delta by 2. Hence its amplitude will be how much? Because this is the probability density function. So f epsilon is the probability density function. So its area under the curve must be unity. So this will be nothing but 1 by delta. How we have calculated? This is nothing 1 upon delta by 2 minus of minus delta by 2. Not to be 1 by delta. Hence, NQ, quantization noise, we can easily calculate as minus delta by 2. Now the limit of integrations will be from minus delta by 2 to delta by 2 epsilon square into the probability density function's value 1 by delta d epsilon, which will come out to be 1 by delta epsilon cube by 3. The limit of integrations will be from minus delta by 2 to delta by 2. And its value will be 1 upon 3 delta square by 8 delta cube, sorry, delta cube by 8 plus delta cube by 8, and it will come out to be del square by 12. As I told you, today in the today's class itself, that is the quantization mass of the PCM will come out to be del square by 12. Somewhere I have written. So I don't remember. Okay. In this slide, you can see here. In this slide, here I have written the quantization noise for the PCM is nothing but the del square by 12. So here you can see the quantization noise, what we are calculating over here, is coming out to be del square by 12. Okay. So this one was our aim is to calculate the quantization noise and quantization error. And this quantization noise arises because of the quantization errors. Okay. So there is a difference between the quantization error and the quantization noise. Quantization error is simply the difference of the output voltages to that of the input voltage of the quantizer. Whereas the quantization noise is the mean square value of that of the quantization error, which is given by del square by 12. And this quantization noise we can represent in another form also, because we know that del is the step size, which is given by twice MP by L. So if you put the value of delta here, then you can write it into another fashion, and L is given by 2 to the power m. So using these expressions, you can represent it in the third form also. So it is up to you that in which expressions you want to remember it. But if you ask to me, then I prefer to remember in this form the other relationship, and we can easily calculate. Now, moving to the next topic. Our next topic is signals to quantization ratio noise. So this I will be discussing in the next class, because this one is the little bit as compared to the calculation of the quantization noise, little bit slightly lengthy as compared to the calculation of the quantization noise. But we will take the same expression for the quantization noise as we have calculated in just in the previous slide. The value of that quantization noise is del square by 12. Then in the next class, we will calculate the signals to quantization noise, and then we will solve one or two problems related to the PCM, and then we will go for the DPCM. So I think in the next class, we'll be able to complete this signals to quantization noise ratio. We'll be able to complete uh, the two or three problems, and then we'll be able to complete the DPCM also. Because in the DPCM, only I need to tell you the basic difference between the PCM and the DPCM, and the basic block diagrams, that how do we generate the DPCM signals, how can we actually demodulate it, you can say, and regenerate our original message signals. For time being, since the time is up, so we can stop our discussion over here only. Meanwhile, if you have any doubt, you please ask me. Otherwise, we can stop our discussions over here. Please.